Welcome to today's webinar covering the 10 essentials to correctly specifying a thermal mass flow meter for your applications and installations. Knowing these 10 essentials will save you time and money up front, not having to rework things or go find specifications later, and more importantly, first time right success when they're installed in the application. So before we get into the 10 specific essentials, I'll give you a little background on and reminder on how a thermal flow meter works, what it is, and specifically what an immersible type thermal flow meter is, so that we're on the same page as to what we're covering today. And then we'll get into the 10 key essentials in detail, and we'll conclude with a summary. So just as a reminder, thermal flow meters, sometimes known as thermal dispersion technology, measure flow by calculating the heat transfer that occurs between a heated sensor and an unheated sensor. The differential temperature being proportional to the flow rate. As the flow rate increases, the differential temperature wants to decrease. So it's almost exclusively applied to air and gas flow applications. And there's two drive techniques used to measure it. One known as constant power, and in constant power, a fixed or a differential temperature is created between the heated sensor and the reference sensor. And as the flow increases, heat is pulled off, and the circuitry is measuring the actual differential temperature. So constant low power is applied, and the product is measuring the actual differential temperature. The other technique that's applied is called constant delta T. And in this case, the same principle applies, except the heated sensor, the power is varied to the heated sensor, and the circuitry is trying to maintain a fixed differential temperature. So as the heat is pulled off the heated sensor, more power is added to maintain a fixed differential. So proportional, as the flow rate goes up, more power is put into the circuit, and the circuit is measuring the change in power required, and that's what's proportional to the flow rate. So today's presentation of 10 essentials is really about immersible type thermal flow meters. And by immersible, I mean where the flow sensors are directly inserted into the air or gas flow stream. By contrast, you may have heard of a product called a mass flow controller. That's also a thermal dispersion technique, but instead of being immersed in it, they actually have capillary bypass tubes, and they pick off a sample of the flow stream. So those are known as bypass or capillary bypass. We're talking about an immersible type that's put directly into the flow stream, and it's put into the flow stream either through a tap point installed on the pipe, or for smaller line sizes, an inline spool piece type section that's inserted as a spool piece into the pipe. In a single point flow meter, the flow element is inserted to the center point depth inside the pipe. The product is looking for a fully developed flow profile at the center point of the pipe. So thermal flow meters, just a reminder of some of just a couple of the advantages of thermal flow meters. They are direct mass flow measuring. They have wide turn downs. We'll talk a little bit about that more later, but 100 to 1 is typical for every thermal flow meter manufacturer, and some have the ability to do more than that. There's no moving parts. There's no orifices to foul or clog up, which makes them inherently reliable with no routine maintenance. And as the pipe size goes up, the only thing that happens for the most part is the insertion length of the flow element gets longer. So the cost does not grow proportionally with the pipe size. So this is a list of the 10 essentials that we're going to cover in detail in the slides that follow. You don't need to write these down. The last slide is actually a checklist in there. But these are the differences between an installation where everything's being questioned and one where you've got a happy camper at the end and everything first time right success. So the first essential I want to cover is probably one of the most important, and many of the other essentials that follow loop back into what is the accuracy performance in the installed application. Consider what the accuracy you need at the installation is what needs to be specified. It will be the initial filter for what product solutions are available. If you're over specifying your accuracy, it's going to narrow the number of choices available, and it's certainly going to increase the cost of the product. I would encourage you, when you get all of the components in these essentials written down, is to ask your supplier of choice for an assessment and an evaluation of what accuracy you can expect in the installed environment. All of us, FCI included, our product brochures are a starting point. They're good for comparing one product versus another in terms of its basic accuracy, but all of us specify the accuracy specification has to do with ideal pristine laboratory conditions. They're typically, it's an air calibration only, and a fully developed profile. Anything not of that is going to potentially increase the inaccuracy. So be sure you're understanding the difference between what's published in a manufacturer's brochure and what the actual installed accuracy will be when all factors are considered. Another consideration in the installed accuracy, and if I really should have probably made this one 11 essentials, a separate category, but that's the temperature and the pressure conditions of the fluid in the application. In your specifications, you not only want to include the normal conditions, but what are the minimum and maximum temperatures and pressures the meter is going to see. Couple of reasons for that. The temperature service available by product and by manufacturer varies tremendously. While most all manufacturers can do up to 200 degrees F, only a handful of manufacturers go beyond that. So if you have a high temperature application, that's going to rule out several manufacturers in there. And you want to be sure the product is capable of operating there. And secondarily is, does the manufacturer's product have temperature compensation that will handle the temperature service that it's going to see? Not all manufacturers' temperature compensation is created equal. Some manufacturers don't even offer it, and they won't tell you that they have it. While other manufacturers will be very explicit about giving you a temperature coefficient specification, which is reflective of how good their temperature compensation will be, while still others offer you a choice of how you get the temperature compensation and over what range. So if there is no temperature compensation, then what is the actual additional inaccuracy that you're going to see over the operating range of the product and the measurement? And less of a factor is pressure. Up to 100 psi, not really much of a factor or influence on the accuracy of a product or the accuracy of the thermal flow meter. Above that can have an effect, so I would always specify in your instrument specification for a thermal flow meter is include not only the normal pressure conditions, but the minimum and maximums the instrument will experience, and let the manufacturer tell you if there's an impact on the accuracy. So next essential is, what is the gas type to be measured? And there's several things to consider here and share with the in your specifications to your manufacturer of choice. As we talked about earlier, thermal flow meters are calibrated for a specific gas because the heat transfer of different it varies by the gas type. So all manufacturers are going to want to know what is the gas composition that you're measuring so that they can calibrate the meter correctly. The other part of that is are the wetted parts compatible? Most manufacturers are making their elements out of stainless steel, but some of it's 304, some of it's 316L. Some manufacturers offer Hastelloy or other more exotic materials. So be sure you're specifying the gas type and whether it's clean or dirty or mixed or there's a moisture content, so that it can be calibrated correctly and the wetted materials are compatible with it. And regarding the gas types is, if you read any of the literature or technologies on thermal flow meters, in all cases, an actual gas calibration will yield superior accuracy. There are such things as equivalencies that are done. They're typically, the instrument would be calibrated in air and then some theoretical adjustment will be made for another gas, and they're all theoretical. Every manufacturer, depending on their calibration capabilities, will do some equivalencies, some more than others. Generally equivalencies just because the cost of outfitting and having cal stands that'll do everything is prohibitive, and also safety considerations. If you've got an extremely hazardous gas, while a thermal flow meter will measure it, there's not a lot of companies that want to flow it or can afford to flow it. So we'll do it. So in those hazardous gases, it could be an equivalency done. But if you can get an actual gas calibration, that will always yield superior accuracy. And if you have a mixed gas calibration, every manufacturer is going to ask you the percentage of the composition, the different, what are the components and in what percentage. A little more on gas composition. I would add, if your gas composition is going to change, you need to specify that to the manufacturer. If the composition, what is the composition now? What could it change to? Those percentages, by how much? And then whether it's predictable and repeatable. For example, seasonality. When I refer to digester gases in the wastewater treatment industry, what the digester gas may be running in the summer is different than it may be running in the winter under colder conditions. And depending on the manufacturer, there's different ways that they may be able to accommodate composition changes if they're predictable and repeatable. So if you know those, you specify those and ask the manufacturer how they're going to accommodate it. Thermal flow meters, as a rule, are pretty tolerant of dirty gases. If there's any residue that happens to be left on the sensors that could alter the heat transfer properties, the recommended practice there is to insert it using a ball valve so that it can be retracted whenever you think the sensor has some deposit on it. Retract the sensor and wipe it off and put it back in. And there's no moving parts or anything that are going to get clogged up. So fairly tolerant of dirty gases. And another component is the gas dry or moist. Everyone can do dry gases. Moisture, and in particular condensate droplets, as you can well expect, if condensate's hitting the sensor elements, then it will disrupt the heat transfer characteristics, and depending on which measuring technique and how pervasive it is, it'll create an erratic reading in there. We mentioned two types of measuring techniques. Constant power is less affected by the water droplets because the one sensor is still heated, so it dissipates some of the condensate. There's other techniques like how the orientation mounting. If you put the sensors in a 4 o'clock or 8 o'clock position to shunt some of the moisture away, manufacturers will be able to tell you that if you can tell them you've got moisture in the line. And a handful of manufacturers have some special techniques depending on how much moisture, how much condensation is in the line. If you know it, be sure and tell your manufacturer that it is a moist gas application, and they may have techniques to mitigate that. Specifying the actual flow range required is pretty normal for any kind of flow meter, and thermal flow meters are no different. And a big advantage of thermal flow meters is that typically a 100-to-1 turn down offers an opportunity for a very wide flow range, and some manufacturers have hybrid techniques that can get you up to 1,000-to-1. But that being said, you still don't want to underspecify or overspecify the flow range and fudge away. In an underspecified application, while most manufacturers will calibrate their meter with 10 to 20% overhead forgiveness, if you will, beyond that, if it's underranged, it's going to be the dreaded words of return to factory for recalibration. By the same token, the overspecifying can lead to additional inaccuracy, unneeded inaccuracy, and added expense or on-site setup difficulties. Taking the calibration points and applying them over a longer range can result in increased inaccuracies unnecessarily. Might also push the manufacturer into quoting you special calibration techniques are required, special processes are required, special flow stands are required, all at additional dollars you wouldn't need to spend. And the other part of it would be to on-site, if it's overspecified, that somehow you're trying to rearrange the product and reset the outputs to the range that's required. So be sure you're specifying the correct flow range that's needed at the application. Response time is another essential that doesn't always come to the forefront, and faster response time does not always equate to better. In a control loop, too fast a response can result in chatter and control components operating too frequently and leading to premature failure. And conversely, if the response time is too slow in a control loop, then the response is going to lag and you'll never get the control that you're desiring. We touched a little bit about this before, but if there's moisture or condensate droplets present in the flow stream, those condensate droplets hitting the sensors, particularly in a constant delta T product, can result in very erratic readings in there. So in that case, too fast a reading, you get erratic results. There's a trade-off potentially with ruggedness as well. The larger mass sensor, larger mass material will be slower. The heat transfer will be slower, but they're more robust and rugged and can handle a rugged handling compared to thinner wall thermal wells. Also, the speed of response can be influenced by that drive technology. Constant delta T technology is generally faster. For the exact same wall thickness of thermal wells, constant delta T would be faster compared to constant power. But then again, constant delta T is more susceptible to moisture erratic readings. And I apologize, it'll be my only FCI ad, I hope, in here. but one manufacturer, FCI, has a hybrid technology where it combines both constant power and constant delta T. So if you have any doubt, specifying AST is the best of both worlds. And that terminates my ad for the day. Another essential to absolutely include in any request for a thermal flow meter quotation or evaluation is, what is the pipe size? What type of pipe? Is it pipe or is it duct? Schedule 40, Schedule 80, square, rectangular, all those need to be included in the specification, and the size. The pipe size will do a couple of things. One, it'll determine whether you have enough straight run in the application, which we'll talk a little bit more in another slide. And size, the initial thing is the size of the pipe is going to determine whether it's a straight insertion type or whether it may need the inline type pre-built spool piece. And the rule of thumb here that you could count on is that the smaller line sizes are going to suggest an inline size over an insertion type. And then you can go the other direction where the line size gets so large that a single point solution just is not going to yield the accuracy and repeatability that's warranted, plus is less likely to have a fully developed profile. So the solution there, depending on the large size of the line, may be that the manufacturer would recommend a multi-point solution in an insertion style meter. So specifying the actual pipe or duct type and size dimensions is critical to specifying a thermal flow meter correctly. So very key to most flow meter technologies, and certainly with thermal flow meters, is the amount of straight run you need to get a highly accurate, repeatable measurement. And it's going to take on, I'm going to cover two things here with this, is where should I be placing the meter, and if I can't place it in the right place, is a flow conditioner appropriate? So thermal mass flow meters, single point flow meters, are looking for a fully developed profile. As I mentioned earlier, they're single point meters that's center point mounted in the pipe. The best practice, recommended practice for thermal flow meters to get a fully developed flow profile is 20 diameters upstream and 10 diameters downstream. If you can design that into your pipe layout beforehand, or you have an existing pipe layout and you can find a spot that has 20D and 10D, that's where you want to insert your thermal flow meter product to get the highest degree of accuracy and repeatability. Failure to have the 20 diameters, 10 diameters is going to be a trade-off for less accuracy and less repeatability. The less straight run you have, the greater the variance, and the greater the variance equals the greater uncertainty in the application. So if your application does not have enough inherent straight run available and you can't live with the inaccuracy because of that lack of straight run, the next thing to consider is a flow conditioner. A flow conditioner is designed to reduce that amount of straight run and produce a repeatable profile in a lot fewer diameters. So what I would encourage you to do is ask your thermal flow meter supplier to provide an accuracy assessment both with and without the flow conditioner, and make the assessment yourself. The other thing I would make you aware of and to consider in your specifications is the pressure drop. Depending on the type of flow conditioner used, pressure drop may be high or very minimal. I do know in most thermal flow meters, the two types that I see offered by thermal flow meter manufacturers, the most common is the perforated plate, which does have a pretty high pressure drop to it. And the other one is the tab type either in a spool piece or in a plate type. And if a flow conditioner is used, then the other thing to be aware is that the thermal flow meter will need to be calibrated for that specific flow conditioner's profile. Not as a match set. It's not a, you don't have to have, it's not a one for one, this flow conditioner with this thermal flow meter, but rather the thermal flow meter's calibration has to be matched to the output, the flow profile produced by that flow conditioner. So just a heads up there to know and specify it early. If you decide after the fact that a flow conditioner is appropriate, then the meter is going to come back to the factory for a recalibration that matches the flow conditioner you're going to use. So sometimes overlooked, at least some aspect, but critical to a thermal flow meter successful installation at the site is what are the ambient conditions at the installation? Is it indoors? Is the meter going to be installed outdoors? If outdoors, is it going to be under a protected shelter or fully exposed to every kind of weather condition that the area is going to have? Those would drive specifications, appropriate specifications for an IP or a NEMA rating, the suitability of the enclosure material, aluminum, stainless steel, plastic, what's acceptable in the installation. And in a process environment, particularly in refineries, chemical plants, oil and gas, hydrocarbon related, is it an explosive proof required application? And if so, both what class, what divisions will it experience it? Does it need to meet? And also which country's standard? The standards vary by region, ATEX in Europe, FM in the US, CSA or FMC in Canada, or IEC, the rest of the world, are just examples. If you're specifying a thermal flow meter that's going on a skid or being exported, be sure the explosion-proof reading meets the destination country's requirements. And sometimes overlooked is whether the sensor and transmitter should be separated from each other. With consideration, is there access to the transmitter electronics for easy wire up, readability if there's an onboard display, service, access ease, and high temperature applications. You certainly don't want to put a electronics transmitter right next to a pipe that's running at 700 degrees Fahrenheit. So if you get into where a remote application, and manufacturer will be able to recommend whether it should be remote, but if you know it's remote, be sure to specify how far apart these are going to be, because there's large differences in capabilities between the manufacturers and within the manufacturer's own products. Some manufacturers may do only 50 feet, while there's others that will do 1,000 feet in there. And it also will affect the product selection and the distance, the number of wires used, and the wire gauge considerations. So if it's gonna be remote, be sure you're putting in your specifications the distance that's required. Well, certainly an obvious essential that you're going to want to put into your specifications is the type and quantity outputs that are required. Is it traditional 4 to 20 milliamp output, single output, or because thermal flow meters are inherently dual function and can produce a temperature output as well, do you need two outputs, one for flow and one for temperature? Is a pulse output or frequency output required to run to an external totalizer or totalizer function in your PLC? Digital communications, if you're going to do digital communications now or in the future, is that output I/O required in the device? And is it strictly an output that's required, or do you want true I/O where you can do configurations and diagnostics and interrogate the device over the bus? There's manufacturers out there that offer it both ways, strictly an output, and others that are true I/O. And unless you specify that on the on your documents, you may not know which it is and get surprised. Further than that, is the device registered by one of these bus organizations? Is that important to your installation, that it be certified, tested, and blessed by the Bus Communication Standard Committee? If that's so, be sure you specify that up front. And last but not least is the ability to change the output type now or in the future an important attribute. Is the customer, is the installation perhaps going analog now but looking to go to a digital bus in the future? It'd be important to specify that now. And do you want that bus communication in the product now? Or the opposite of that is you've got a digital bus communication that you want, but you're a little uncertain, and it's possible that either in downtime or you're going to get cold feet and want to go back to traditional 4 to 20 milliamp analog output. Are both of those outputs in the product, or can the product be changed? Very much a consideration you'll want to put into your specification. So let's talk next about the compatible process connections as being an essential requirement of specifying a thermal flow meter as well. Knowing the type of it, how it's going to be inserted into the pipe, what type of fitting, is it an NPT, a compression fitting, a flange? All those things need to be known up front. Various manufacturers do not offer all of those, and it is one of the worst possible things to get the product into the field and find out the wrong mating process connection is out there, because that means the dreaded word of rework. Either the flow meter product is the connection is going to get reworked, or you're going to get the pipe fitters union out there to rework the process connection. Another consideration in that process connection is there enough room around the pipe to, particularly with an insertion type flow meter, to insert the full length of the product in the enclosure in the pipe. I've seen too many instances where there was adjoining pipes above or right next, running parallel right next to the product, where the pipe couldn't fit in, or even worse, it was running along a corner in a ceiling, and the only place you could put the meter was at a 90-degree angle on one side. So be sure there's enough room to get the full length of the insertion plus the enclosure into the process penetration hole. Another subtle configuration that sometimes gets overlooked is if you're going to use a ball valve on an insertion meter, which is a very popular thing to do, is you have to make sure the ball valve, the length of the ball valve itself, is added into the insertion length of the probe. Seen instances where people get a 6-inch length probe and then put a 4-inch ball valve on it and expect to insert it to centerline in an 8-inch pipe. Not going to work there. So know up front and tell a manufacturer, put on your specifications that you're going to use a ball valve and how long that ball valve is, so that the insertion length comes out correctly. And if it's an inline, what is the length of pipe section available? Is how much you're going to have to cut out and make room to put that in there. I know with FCI products, when we put a Vortab flow conditioner run in there, the spool piece section is 9 diameters, and we'll tell you that up front. Other manufacturers, we also have products that have a simple T that's very small, that no flow conditioner and can drop in pretty easily. So what type of pipe fitting, what is the process connection? Is there enough room to fit it in. Consider all those mechanical constraints. And last, but certainly not least, in the specifications and callouts for thermal flow meters is, does the application require certain pedigrees, certifications, documentations? The time to call these things out is right up front, not after the fact. If you need pressure tests or material traceability, oxygen clean, those kind of things, those things have to be known by the manufacturer up front so that you get the product at the end that has all those pedigrees and information you're looking for. And not all manufacturers can provide everything that might be required. So they may have your product, but not your tests and certifications. So getting those documentation certifications specified upfront and early avoids surprises at the end. If there's requirements for particular environmental or explosion-proof requirements, like we talked about on the prior slide, is what are the specific approvals required, what division, what class, and for what country. That will assure you get the right product for the right place. If it has particular industry application or industry certifications like 3A in the food dairy market, Germansher-Lloyd if it was a marine application, is it an EPA, US EPA, or other countries' EPA requirements? And the other thing I would tell you is that not all certifications are alike. Is explosion-proof ratings, for example. Some manufacturers are just doing a buyout enclosure. Is a rating just on the enclosure adequate, or is it a full instrument certification that you're looking for? Outputs, digital bus comms, some of the bus comm organizations have their own testing facilities and will validate the product against their standards. So are you looking, for example, for just heart compatibility, or do you need a heart certified IO product with documentation to support it? And on some of the other things like declarations of conformity, other conformities, you're looking for, is independently certified required, or is self-certified adequate? So in conclusion, if you've got the answers to those 10 essential questions, that equates to a very productive and efficient dialogue between you and a supplier. If you're an engineering firm, you and your client, and it'll save both of you time answering these 10 questions, having the answers to these 10 questions up front. If you don't answer these 10 questions, then you're missing information, and at some point it's going to be go back and get this information. And without the information, then you're going to end up with possible undesired consequences and surprises at the end of the line. Further, you overspec the product. If you're overspeccing it, that's going to equal unnecessary dollars, a higher cost than you really need to spend. And if you underspec it, the outcome is going to be poor installed performance, shorter service life, and or unsafe installations out there. So I promised at the end there was a check. You didn't need to write the stuff down. Here's a checklist summarizing everything. If you follow that, provide that to your customers, be they internal or external, and your suppliers, everyone ends up happy, and you've got the highest performing product that meets the application with the longest possible service life and the most safety in the installation. Thank you very much. With that, we'll end the presentation and see if there's any questions.